The next topic is titrations between weak and strong species. So what I've got here for an example is the titration curve for a weak acid with a strong base. And specifically, this is propionic acid. So that is simply acetic acid with one extra carbon in it. And this is initially a 10th molar solution of it. And for comparison, the titration of an equal volume of 10th molar strong acid, say for example HCl, is shown here in this dotted line. So there are a couple of differences to note. First off, at the very beginning, you'll note that the pH of the strong acid, strong base titration curve starts out a lot lower. It's a strong acid. Every HCl or every H103 molecule creates one hydronium, so this is to be expected. Meanwhile, propionic acid is a weak acid with a pKa of about 4.89. So even though it's the same concentration, most of the propionic acid doesn't ionize to form hydronium, so the pH is going to start quite a bit higher. In this case, a full 2 units higher. The exact difference depends on exactly what acid it is. And you got a case where the pH starts to change fairly rapidly, and then the rate of change kind of stops a little bit, and then starts to go back up again. So a few other differences. So for a strong acid, strong base titration, the pH is going to be 7 at the equivalence point, because essentially you've got water and a neutral salt at that point. But at the end point of the weak acid strong base titration, it is actually a little on the basic side. Why is that? Well, in this case, what you've created, what you have at this point now is a whole bunch of the conjugate base of the original strong acid. So you've got a whole bunch of propionate is the name of it, which is itself a weak base, so the pH is a little high. And then after that, there isn't really much difference, because the pH after the equivalence point in both cases is dominated by just the excess hydroxide, which doesn't matter, which is the same either way. Now, you might ask yourself, do I have to use a whole different set of indicators because your pH at the end point is a little higher than 7? And here's a dirty little secret. Phenolphthalein actually doesn't change pH until pH of about 8, or doesn't change color until the pH is about 8. But look how, if you look for both of these curves, how strong or how sharply this curve is rising around the equivalence point, whether it's for the strong acid or the weak acid titration. The change in volume between pH 7 and the color change range of the phenolphthalein, which is about, it starts at about 8, 8.2, is negligible. It is within the experimental error of even a professional, someone that does this for a living, much less, a Gen Chem student that has only done it a few times in their life. So, no, the fact that phenolphthalein changes color at a little bit of a basic pH, not a problem, because the volume, that extra volume here is negligible. It's within experimental uncertainty of the burettes that you've got. All right. So, and because the species along the line, the weak acid and the propionate, are themselves, acids or bases, the calculation for various of the pH for various points along this curve is a little different than it is for the strong acid, strong base ones. So we're going to spend some time actually going through them. So here's our setup. We're just going to work through an example. So I'm going to use the ubiquitous vinegar as an example. We have 100 milliliters of it, and it is half molar. And we're going to titrate it with 0.2 molar sodium hydroxide. So we're going to do a couple of things. We're going to determine the pH at the beginning before we actually start to titrate. We're going to calculate the pH at some intermediate point. And we're going to calculate the pH at the equivalence point. So the first thing is a review of stoichiometry. So let's figure out what the what the equivalence point is, and then calculate the pH before we start. All right, just to review, the definition of equivalence point is the point at which the amount of acid is equal that we had present in our flask is equal to the amount of base that we have added. And hopefully you remember this one very important relationship that I told you would be very important, and that is that concentration times volume equals amount, or in the language of the units that we usually use, liters times molarity equals moles. And so we have 100 milliliters or 0.1 liters of acetic acid. I told you it was 0.5 moles per liter. And that's going to be equal to the amount of base that we need times its concentration point, which is 0.2 moles per liter. And if you work all that through, you get a endpoint volume of 250 milliliters. So this would end up being a fairly large burette, but they actually exist. The next part of this exercise was to calculate the pH of the acid solution before you start to add base to it, before the titration starts. And so at this point, it's just a plain Jane 0.5 molar acetic acid solution. And at this point, this calculation should be fairly straightforward to you. So you've got equilibrium between the acetic acid and water and acetate and hydronium. So just make up your standard ice table. This is in molarity, so we have half molar acetic acid, none of the acetate and the hydronium, which means we'll lose some of the acetic acid to create some acetate and some hydronium, giving us these symbolic concentrations at the end. And from there on in, it is simply algebra. And here's one more chemistry thing. So we've got the Ka is equal to the hydronium concentration times the acetate divided by the acetic acid concentration. Plug in the the symbols that we've got, so x squared over 0.5 minus x. We can approximate that denominator to just 0.5 and set that equal to the Ka, and so Ka for acetic acid happens to be 1.8 times 10 to the negative fifth, which gives us a value of x of about 3 times 10 to the negative 3. So those are our acetate concentrations. So the initial concentration didn't change by 5%, so it changed by just a few, so no big deal. And that gives us a pH of about 2.52 to start with. All right, and now onto the actual titration.